Good afternoon. We will start today the study of linear programming problems. And in particular, we're going to talk about the graphical method to begin with. And we're going to make use of what we learned last time in terms of solutions of linear inequalities or a system of linear inequalities, except that we have now on top of that an objective function to minimize or maximize. So as usual, take some time to actually write down what's already given here on the page. And then we will start with commenting on how we approach the problem. So all linear programming problems will have two parts. You will have a number of constraints, which basically is a number of inequalities. So you will have always a system of inequalities. Those are the conditions or the restrictions of the problem. Because remember, in each application, like for example, a business application, you always have certain conditions or certain constraints that you have to abide to before you think about maximizing or minimizing an objective function, which is, for example, a profit or a revenue function, or minimizing the cost, for instance, depending on the case. There are always limited resources or limited conditions due to various factors. So for example, suppose that there is a maximum capacity of a line of production. So no matter how many different items you want to produce or of different types, you can have more than 1,000 in a day, let's say, if that's the capacity. Maybe there is a limited amount of the money that you have at your disposal for the equipment or the material necessary to make your product, and so on and so forth. All of these are in practice inequalities. So you will have a bunch of inequalities, two or more, that will describe these constraints. And using the graphical method, remember from the previous section, you could visualize the solution of these inequalities as a region in the plane, meaning that whatever you want to produce, whatever the solution is for the objective function, it has to be within that domain or feasible region given by the solution of those constraints. What we have on top of that is the so-called objective function. All linear programming problems will attempt to minimize or maximize a function. Again, depending on the context. If your function is a cost function, obviously you'll probably want to minimize that. If it's a revenue or a profit function, you want to maximize that subject to these constraints. So before we tackle a full example from top to finish, let's talk about how this objective function looks like and some important remark related to how the graph of this type of function looks like. So suppose, for instance, in your application, you want to make two types of product. And then X is the number of units of one type, and then Y is the number of units of the second type. In all of these problems in which we use the graphical method, we deal only with two variables, because for more than two, the graphical method is not practical. So you have these two types of products, and let's say you want to maximize the revenue, and you can sell them for $1 each of type 1. Let's actually name them. So one type, let's say this is type A, this is type B. Okay, so $1 each for a unit of type A. And let's say we have $2 each of type B. Okay, so these are the selling prices. And you want to maximize, so the goal is to maximize revenue. We deal with linear applications, linear equations, so all of these problems will lead to linear formats of various equations or inequalities. So if I want to maximize the revenue, then in this particular case, the objective function is going to be R, let's call it R from revenue, is going to be equal to $1 each times the number of units plus $2 times the number of units of the second type. Okay, so in short, R is going to be X plus 2Y. So that's an example of an objective function, and in this case, again, we want to maximize it. So that's the goal. What I want to focus on this part of the lecture is to see how the graph of this objective function looks like for various values of R. So you will see why that's important for later. So let's even write it down as a question mark or an observation in the form of a question. How does the graph of the objective function looks like for various values of R? And let's actually write down 3 examples, starting with the most pessimistic one. For example, the very worst outcome is to have 0 revenue. Let's say you sell nothing essentially, and the revenue basically is 0, which is obviously not what you're gonna get in the end, but that's like the minimum boundary, so to speak, of what's possible in terms of the solution of a linear value problem. So let's actually graph 3 situations, namely R equals 0, as I said, R equals 1, and R equals 5. So that means I want to plot the equations x plus 2y equals 0, x plus 2y equals 1, and then x plus 2y equals 5. So these are 3 possible values for the revenue, 3 possible objective functions. So in other words, for example, if your revenue, if you want to get a revenue equal to 5, then the number of items of each type can be any combination that will give you x plus 2y equals 5. Now, and of course, we're going to assume later x and y is positive because you cannot make negative products, but for now, let's not worry about that. One more thing I want to do before I actually sketch this, why don't you take a moment, in fact, pause the video and do it as an exercise and check with me. Write each of them in slope intercept. And remember, to do that, you get y by itself. So if you look at the first one, if I move y over, I get y equals minus 1/2 x. In the second one, I get 2y equals 1, or let's say 1 minus x. I'm going to start with x later. If I divide by 2, that's minus 1/2 x plus 1/2. And finally, the last one, 2y equals 5 minus x. And again, if I divide by 2, I get minus 1/2 x plus 5 over 2. These are the objective functions corresponding to the revenue 0, revenue 1, revenue 5, each of them in the slope intercept form. So one important remark, which we should write it down here, is that the slopes are all equal. And equal to, in this particular case, minus 1/2, right? So remember, in the slope intercept form, the coefficient of x is equal to, gives you the slope. So all of these lines for various values of R will be parallel to each other. That's very important so you understand what comes later. So with this in mind, let's actually sketch these 3 lines. We're going to do it over here in this corner. So let's do the coordinate system. That's enough. So this is x and this is y. And let's sketch these 3 lines for these 3 possible values of the revenue. So the first one, 2y minus x, x plus 2y equals 0. It goes to the point 0, 0. That's one obvious point. And another point let's try to do this in our minds without writing on a scratch paper. So, and we should plug in easy values to do that. Let's say y equals 1. So if I put y equals 1 over here, then x is minus 2. Minus 3 and 1. So that's another possible point for the line that gives me the revenue equal to 0. Okay, and I'm going to even write it down near the line that this is corresponding to r equals 0. Right? It's x plus 2y equals 0. That's when the revenue is equal to 0. Now notice that as I plug in, as I sketch revenues with higher values, so better outcomes in other words, you will see that the next line is not only parallel to the previous one, but on top of it. So as you get a bigger revenue, the line that represents that revenue is on top of the previous lower revenue. So x plus 2y equals 1, one possible point. Let's write the intercept, right? So if y is 0, x equals 1 over here. And if y is 1, so let's do this 0 actually. So like I said, y is 0, x equals 1. If x is 0, y equals 1/2, which is over here. Okay, so these are the 2 points on the line. 1 and 0, and 0, 1/2. So very close to the previous one, but on top of it. Let's see, I try to make them to look parallel. And this is r equals 1. All right, the other one will be a little bit further up, right? Because I put the revenue 5 on that one. So x plus 2y equals 5. Let's look at the last one. If y is 0, x equals 5. So it's going to be further to the right over here. Let's say this is 5. And then finally, another point. Let's see. Let's make it actually... well, let's do the 0 as well. So if x is 0, y equals 5 over 2, which is 2.5. So 2.5 is maybe over here. Okay, so anyway, it should be parallel to the previous two lines. So this will be 5 over 2. And again, this line now corresponds to r equals 5. All right, so that's one important remark. Let's actually name these, number these remarks. That's remark number 1. The remark number 2, the lines corresponding to higher values or to larger r values are on top of lower ones. In other words, you could think in terms of a graphical approach. If you want to maximize the revenue, you just have to go up with parallel lines. So moving upward with parallel lines, that gives you another option of the revenue. So you could go up indefinitely, of course, and you'll get a bigger value of r. But remember, in these linear programming problems, we will always have a system of inequalities, the actual constraints, which will give you only a narrow part of the plane, the so-called feasible region. And at this point, let's actually take an example of that possible feasible region. And then we're going to move on to an actual example with actual constraints. But suppose that the constraints in this problem will give you in the end the interior of a region in the plane, just like in the problems that you worked on when you dealt with the previous section. So suppose, for example, that the feasible region, let's sketch it here, let's see if we can fit it in. Let's see, I want to have x equals 3, so it may be further up here, like that. And then I want to go to the right all the way up to 6, actually. So basically right now I'm sketching a possible feasible region that can come up from those inequalities. Okay, so suppose the interior of this quadrilateral, and let's actually fill it in to indicate that that's the solution of the constraint, represents the feasible region. And label the corners in the following way. So suppose the lower left corner is of coordinates 3, 3. This one, let's say, is of coordinates 6, 3. This one is of coordinates 7, 4. And let's say the one above here is of coordinates 3 and 5. So obviously you want a revenue function that overlaps the constraint. So suppose this region is the feasible region corresponding to the constraints on the problem. Okay, that comes from, again, a system of inequalities. Just for now, let's not focus on those inequalities that led to this feasible region, and imagine that that's the feasible region. So that is the key thing, okay? How do I maximize the revenue function? So right now, these versions, these three values won't do, because you can only have a solution if it overlaps with the feasible region. So the R line must overlap with the feasible region. Because all solutions must lie in that feasible region. Those are the constraints. Remember, you can only have a solution as long as it sits in one of these points inside this quadrilateral. And because your goal is to maximize it, you basically want to go and raise this line, so move on with parallel lines until you hit the constraint domain or the feasible region. So for example, as I move upward, pay attention over here, this is a possible solution because I have already an overlap with the feasible region. And obviously the value of R here will be bigger than what I had before. I don't know what it is, but certainly bigger than 5. But now because you want to maximize R, you can move upward and get bigger values, right? So for example, I can do another one parallel to the previous one, and that'll give me a larger R. As you go on top of the previous one with parallel lines to the previous R, you get better and better values of R. All that matters is to have overlap with the feasible region. And let's do another one which is even better. So for example, this one that I'm sketching right now gives you an even better value, right? And you still have possible values because it still overlaps the feasible region. And the key thing to notice is that you can keep on going up and keep on getting larger and larger values of R until you hit a certain corner. In this particular case, it will be 7, 4. And that'll be basically the best you could do. So that is basically the maximum possible of the revenue subject to these constraints. Because any parallel line on top of this one will leave the feasible region, and you're not allowed to do that, right? You have to stay inside the feasible region. Any lower than that, that's not the maximum, right? I mean, lower than this corner, it's possible, you have feasible points, but that's not going to be the maximum revenue. You want to maximize that function subject to the constraints. And you notice that this always happens at the corner of a feasible region. So finally, let's write down the most important remark for this page at least. The maximum, or even minimum for that matter, we'll talk about that also because the same idea works for the minimum. The maximum or minimum of the objective function is attained at a corner of the feasible region. It is always a corner. And the good news, you will see that you don't even actually need to guess what that corner is, like we managed to do here, all you have to do is basically evaluate the objective function at each corner and just pick the minimum or the maximum. Notice that in this case, we could actually check that indeed that corner gives me the maximum. So let's plug in actually the corner into the objective function. So remember the objective function was x plus 2y. So in the corner 7, 4, that was 7 plus 2 times 4, that's 15. And you'll notice that each corner you plug in, any other corner will give you a lower value. So for example, if I plug in the corner 3, 5, that's going to be 3 plus 2 times 5, that gives me 13, that's a lower value. If I plug in the corner 6, 3, that's 6 plus 2 times 3, that's 12, that's a lower value. And then let's check the other one, 3, 3. So if I plug in, obviously, if I plug in 3 and 3 for x and y, that's 9, so obviously a lower value. So as it happens, this corner gives me the maximum. And so in practice, as you will see later, we don't have to sketch these lines, parallel lines. All you have to do is to evaluate the objective function at a given corner. But this is the reason why. Each of these objective functions for various values are nothing but parallel lines. And as you draw these lines to overlap with the feasible region, the one that gives you the maximum always ends up at the corner of a feasible domain. Why at the corner? Because, you know, any higher than that, it will leave the region. Any lower than that, that means you can get better than that. I mean, it's not the maximum or the minimum. So on the next page, we're going to do a full linear programming problem from top to finish, starting with the actual constraints. And then we're going to talk about two objective functions just to see that sometimes it's not actually clear from the beginning which corner gives you the maximum or the minimum. Because sometimes the graphing method can be unreliable if you don't sketch carefully these lines. But like I said, the good news is that you don't actually have to sketch the lines, because once you know that the objective appears at the corner, all you have to do is to compute those corners and then evaluate the function at each corner and pick the one that maximizes or minimizes the function. So stay tuned for the second page. Okay, so let's go over this example. And this is basically two problems in one, right? Because I want to show you the effect of choosing a different objective function. So let's say you want to maximize the revenue, just like before, but you have two scenarios. Like, for example, in this case, you want to make X, the first type of product, more expensive. Let's say it's $10 a unit and $1 the other one. And then in the other scenario, you want the first one to be $1, right? The coefficient of X, and the other one $8. But the constraints are the same. So this system of inequalities represents the constraints of the problem. I mean, if you we're gonna get to word problems later for sure, but if you want to figure out, for instance, the meaning of these types of conditions, for example, the first one could mean that you can't make more than 5 times X products than Y products, or you cannot make more than 3 times Y product than X products, or whatever constraint in terms of the number of units you can make, depending on the equipment you have. There's lots of possible interpretations or reasons for constraints of this type. Or maybe it has to do with the manpower, whatever. The last condition could be an upper bound on the cost, for instance. Let's say you have some per unit cost, and then you have to have a cap per day, let's say, if this is a linear programming model for a day of activity, all sorts of things. So there are possible interpretations for each of these inequalities. What's important from a mathematical point of view is that all of these inequalities will give you the feasible region. So that's your starting point to solve the linear system of inequalities in order to find the feasible region. and importantly now, its corners. Because we know already that the solution will appear at one of these corners. So we may want to write these inequalities in some sort of standard fashion, like in the form of ax plus by less than or equal to c or greater than or equal to c. That's not strictly necessary, but just to keep it kind of consistent with many other problems. So let's move the terms to the right. So we have 5x minus y greater than or equal to 0. That's one constraint. X minus 3y less than or equal to 0. And 2x plus y less than or equal to 7. And the positivity condition, you can just deal with it at the end by simply looking at the first quadrant. So you take into account x positive, y positive just by looking at the first quadrant and ignoring the rest when you look at the feasible region. So remember how we solve the linear system of inequalities? You sketch the lines corresponding to each inequality. 5x minus y equals 0. Line 2 is x minus 3y equals 0. Line 3 is 2x plus y equals 7. And let's establish a couple of points for each. So for example, 1 point, if x is 1, well, actually, let's do the 0, 0, like we did before. So 1 point is 0, 0, obviously. Another point, let's say x is 1, that makes it 5, 1, 5. 0, 0 is also a point of on the second line. And let's say I plug in 1 for y, and x is 3. So 3, 1 is another point. Line 3, let's say if x is 0, y is 7. So 0, 7 is one possible point. And if y is 0, x is 7 over 2. So we're going to do this here on the left side. 0, 0, 1, 5. So let's say this is 1 and this is 5 over here. When you do these problems, by the way, it's better maybe to label each point by its pair of coordinates, because when the time comes to plug in each corner into the objective function, it's easier to see what you have to plug in. So when the time comes to sketch the, to label the corner, we're going to do that at that time, right? So that's L1. L2 goes to the point 0, 0, so also 0, 0, and 3, 1. So let's say this is 3, and this is 1 over here. So this line is further down. All right, so let's call this is L2. And the other line goes to the point 0, 7, 7 over 2, 0. So 0, 7, I gotta make this a little bit up here. So 7 should be over here. So that's 0, 7. And the other point is 7 over 2, which is like 3 point something. And 0, let's say 7 over 3 is over there. And so that's the other point. Right, so that'll be line number 3. Now remember, we need to produce the corners. But actually, before we do that, let's look at the feasible domain, right? Because remember, we have inequalities. So going back to line 1, that has to do with the first inequality. So remember, we need to plug in a test point in one side of these lines, so we know whether we take into consideration the region above or below the line. Now, let's test the region below the line. So if I look at, let's do it on this range here. So if I look at the test point below the line, let's plug in 1, 0. So below line 1, 1, 0 is obviously one test point. So if I plug in all the way into the inequality 1, 0, 5 times 1 minus 0, obviously we get a true statement. 5, 1 times 1 minus 0 is positive. So below line 1 is the solution of that inequality. So keep that in mind. We're looking, because I don't want to make a mess on the picture, we're looking at the region below L1. For the second line, L2, let's look again at the point below that line. So I'm going to pick a test point 3, 0 for that line, for that inequality. So test point 3, 0, plug it in into the inequality, and is 3 minus 3 times 0 less than or equal to 0? No, 3 is not less than 0, so that means you're looking at above L2. That is the solution of that second inequality. So right now we are below L1, above L2, and finally a test point for line number 3, the easiest one we can pick is 0, 0, and that will test the region below L3. Going back to the inequality, plug in the test point, 2 times 0 plus 0 less than 7. That's true, so that means the solution of that is below L3. Okay, so all in all, the feasible region is below L1, above L2, below L3. And so if we look carefully to the picture, that means we basically have the interior of this triangle. Right, that's the feasible region. All right, so the next thing is to label the corners of this feasible region. So one corner is already given, 0, 0. In order to find the corners, the other two, we need to come up, or we need to solve two systems. We need to see where the line 2 and line 3 intersect. So the equation of line 2 is x minus 3y equals 0. So line 2, line 3. And line 3 is 2x plus y equals 7. Let's eliminate y. I multiply the second by 3. So I have 6x plus 7y plus 3y, I'm sorry, equals 21. Add the 2. That gives me 7x equals 21, which means x equals 3. Go back to the second equation. If x equals 3, then y is 7 minus 6, which is equal to 1. So the corner over here is 3, 1. Label the corner immediately, because that's a candidate for the maximum or minimum. The other corner left to find is between the intersection between L1, 5x minus y equals 0, and L3, 2x plus y equals 7. We can eliminate y by simply adding the 2. So 7x equals 7, that makes x equals 1. And we can go back to the second equation and plug in 1 for x, and that gives me y equals 7 minus 2, which is 5. By the way, by coincidence, I plugged in 1, 5 before, but that's just a coincidence because it so happened that I plugged in that point when I sketched the line. Because when you sketch the line, the points you plug in are not necessarily the corners. That's why you need to solve the system here. So this is 1, 5. So the hard part is kind of over in these problems, because now to maximize your objective function, all you got to do is to plug in each of those objective functions into each of these corners. So let's do part A. And by the way, you can actually speed up the process by skipping the corners that obviously won't give you any solution. I mean, it won't give you the maximum solution. So obviously I'm not gonna, I mean, 0, 0 is not the objective. I mean, it's not the maximum. You can get better than that, right? So the objective function is again 10x plus y. Remember, we started with that, that objective function. 0, 0, 1 give you the maximum. Let's check between 1, 5 and 3, 1, which one gives you the maximum. So check 1, 5. So if I plug in 1, 5, I get 10 times 1 plus 5, that's 15. Then check the other corner, 3, 1. And in that case, the revenue will be 10 times 3 plus 1. That's going to be 31. So clearly, this is basically the maximum, right? So in part A, the maximum revenue is going to be 31, and it is attained at x equals 3, y equals 1. So in this optimization problem, you will say, I'm going to have to make 3 units of the first type and 1 unit of the second type in order to maximize the revenue, which is $31 or whatever the units are going to be measured here. And like I said, you can't really predict unless you look carefully at the graph which corner will give you the maximum, right? So notice if I change the objective function, so let's repeat the same process now with the other objective function, x plus 8y. Again, I'm going to skip 0, 0 because obviously that's not going to be the maximum. And when I check in the corner 1, 5, now I get 1 plus, so the revenue is 1 plus 8 times 5, that's 41. And when I check the other corner 3, 1, the revenue will be 3 plus 8 times 1, which is 11. And obviously the maximum will be attained at the other corner at 1, 5. So for this particular revenue function, you want to make 1 unit of the first type and 5 units of the second type in order to end up with the maximum revenue, which is equal to 41 in this case. So you don't need to sketch the revenue. Again, I want to emphasize one more time, one doesn't need to sketch the revenue line. We did that sketch just to justify why the objective is going to be maximized at the corner. So we don't need to mess with that. I'm going to just show you right now visually again why that's the case. But again, in practice, all you need to do is to sketch just the feasible region, the corners, and then evaluate the objective at each corner. Now, the reason each objective function gives you different corners as a maximum is because of the shape of that line. So if you sketch the line for part A, that's a much steeper line. So when you sketch revenue equal to 0 for part A, I'm going to make a mess here just to illustrate. You'll get a steep line, and as you increase the value of R, notice that you skip the first corner, and then you end up leaving the feasible region on the corner 3, 1. And on the other hand, if I sketch the line corresponding to part B, x plus 8y, that's a much less steeper line. It goes like that. And as you go with higher and higher values, now that line skips the corner 3, 1 and leaves the feasible region when it comes and touches the corner 1, 5. So which corner it leaves from the region, I mean, what I'm saying is the corner that is the last one as you move on with higher and higher values depends on actually the slope of this line, depends on how steep that slope is. And that's why it can be actually any of these corners, and it depends also on the shape of the feasible region. But once again, you don't need to do this mess. You don't have to draw these parallel lines. All you need to draw is the feasible region and its corners and just evaluate each corner with an objective function. And I think that's it for today. I will probably, depending on the case, I mean, I'll think about it. It's probably going to be another part of this section, just because we're gonna have to deal with some word problems as well, and just for extra practice on linear programming with the graphical method. But for now, that's it for today.